96%. That is how much of the moon is about to slide into darkness this week, and it is happening so close to totally dark that most people watching will swear they saw a total eclipse, even though they technically did not. Nobody alive has watched this exact shadow fall on this exact night, because a moment like this one does not repeat. Stick around, because I'm going to walk you through exactly what happens, hour by hour, and why scientists say this is the best lunar eclipse anyone on Earth will see until the very end of 2028. And before we get into it, hit subscribe now if you want to know the second any sky event like this one is about to happen, because I post the exact viewing times before every single one. Here is the short version. On the night of August 27th, sliding into August 28th, 2026, the full moon is going to drift almost entirely into the shadow of our own planet. Not a sliver of it, not a bite taken out of one edge. Nearly the whole face of the moon, all at once, wrapped in Earth's shadow. And the strange part is, officially, this is not even called a total eclipse. It is called a partial eclipse. That single word, partial, makes it sound like the smaller, lesser cousin of a total eclipse, the kind of event you might skip. But the number tells a very different story, and once you hear it, you will understand why so many skywatchers are clearing their calendars for this one. Let us go back to where this story actually begins, because to understand why this particular moon is such a big deal, you need to unlearn something almost everyone believes. Most people think a lunar eclipse happens every single full moon. It feels like it should. Every month, the moon lines up on the opposite side of Earth from the sun, full and bright. So why isn't the moon swallowed by Earth's shadow every single time that happens? The answer is that the moon's path around Earth is tilted, just slightly, like a record spinning a little crooked on a turntable. Most months, the full moon passes just above or just below Earth's shadow and completely misses it. An eclipse only happens on the rare nights when the tilt lines up just right, and Earth's shadow and the full moon meet in the same patch of sky at the same time. For most of this century, eclipse watchers have treated partial lunar eclipses the way a coach treats the backup player. Total eclipses get the highlight reels, the packed viewing parties, the countdown videos. Partial eclipses usually get a shrug, because usually only a small notch of the moon dims while the rest stays bright and boring. This one flips that assumption on its head, and by the end of this video, you will see exactly why it earns a spot right next to the totals. The first surprise is the number itself. Scientists measure how deep an eclipse goes using something called magnitude, which just means how much of the moon's face gets covered by Earth's darkest shadow, the umbra. A magnitude of 1.0 would mean the entire moon is swallowed, a full total eclipse. This week's eclipse comes in at a magnitude of about 0.93, which means roughly 93 to 96% of the moon's face gets pulled into that dark core of shadow. Picture almost an entire dinner plate covered by a shadow, with only a thin, bright crescent left glowing along one edge, like a fingernail of light on an otherwise vanished moon. Scientists expected going in that this eclipse would land somewhere in the ordinary middle range for partial eclipses, dim but forgettable. What they actually calculated was a shadow depth so close to total that from the ground, with your own eyes, you likely will not be able to tell the difference. That is the compression right there. A partial eclipse, deep enough to fool a trained observer into thinking they watched a total one. Here is a comparison that makes that number land. Imagine painting a dinner plate white and then covering all of it except a strip along the rim about as wide as your thumbnail. That thin strip is the only part of the moon that stays in direct sunlight this week. Everything else slides into shadow, and it happens slowly enough that you can watch the shadow crawl across the moon's face in real time, like a slow-moving cloud made of darkness instead of water vapor. The second finding changed the way scientists describe this whole event. Full moons in August are nicknamed the sturgeon moon, an old name that comes from Native American and colonial fishing traditions, back when a certain large freshwater fish called the sturgeon was easiest to catch in North America's Great Lakes at this time of year. This year, that same sturgeon moon is the one stepping into Earth's shadow. The exact moment of the full moon lands at 4:18 in the morning, UTC time, on August 28th, which for most of the United States falls a little after midnight on the 27th going into the 28th, right in the thick of the eclipse itself. The third discovery is the one that puzzled casual skywatchers the most, and it has nothing to do with the shadow itself. It has to do with who actually gets to see it. According to the tracking organization Time and Date, which has calculated eclipse visibility for decades, about 987 million people, roughly 12% of everyone alive on Earth right now, will be able to watch the entire event from start to finish. Around 1.3 billion more will catch at least the deep partial phase. The best seats in the house belong to North and South America, where the eclipse happens high in a dark night sky. Europe and Africa catch it low on the horizon as the moon is setting, and much of Asia and Australia will already have daylight by the time it starts, meaning the moon will simply be below the horizon, out of sight, while the shadow does its work unseen from those parts of the world. Let's zoom out for a second, because the distances involved here are almost impossible to picture. The moon sits about 239,000 miles from Earth on an average night, which is close to 10 times the distance you would travel driving around the entire planet at the equator. Now zoom back in. The shadow falling across that faraway moon this week is being cast by something as ordinary and close as your own front porch light casting a shadow behind a basketball held up in your backyard. Earth is the porch light, the moon is the basketball, and the shadow stretching across 250,000 miles of empty space follows the exact same rules of geometry as the shadow stretching across your driveway. Quick question for you before we keep going. Have you ever actually watched a lunar eclipse happen live, start to finish, with your own eyes? Drop a comment and tell me where you were and what it looked like, because it genuinely helps me figure out which sky events you want me covering next. Now let's get precise, because the exact timing of this event was not guessed at. It was calculated years in advance, down to the second, using the same orbital math that space agencies use to plan spacecraft landings. NASA's Goddard Space Flight Center keeps a public catalog of every solar and lunar eclipse from thousands of years in the past to 1,000 years in the future. That catalog was largely built by a retired NASA astrophysicist named Fred Espenak, who spent decades of his career doing nothing but calculating exactly where shadows fall in space. Skywatchers still nickname him Mr. Eclipse, and the numbers in this video trace straight back to that kind of work. Here's the timeline. In universal time, the standard clock astronomers use, so the whole world is talking about the same moment. The faint outer edge of Earth's shadow first touches the moon at 1:23 and 55 seconds UTC. That part is subtle, barely noticeable, like a light dimmer being turned down one click at a time. The real show starts at 2:33 and 48 seconds UTC, when the moon crosses into the dark umbra and a visible bite appears to grow across its face. The deepest point of the whole eclipse, the moment when 96% of the moon sits inside that shadow, arrives at exactly 4:12 and 49 seconds UTC. The moon fully exits the dark shadow at 5:51 and 55 seconds UTC, and the last trace of the faint outer shadow fades away by 7:01 and 41 seconds UTC. Convert that to your own time zone, and you have got a start-to-finish window of a little over 5.5 hours. This is also where the sensory part of the night kicks in, the part no chart or number can fully capture. As the shadow deepens, the brightest part of the moon shrinks down to that thin fingernail of light, and the rest of the lunar surface does not simply go black, it glows. Sunlight bending around the curve of Earth's atmosphere gets filtered the same way a sunset filters light, stripping out the blue and letting the red and orange wavelengths bend around the planet and land softly on the moon. So instead of vanishing, the moon slowly shifts into a deep copper, rust, or blood orange color, hanging there in total silence, while everything around you on the ground stays completely unchanged, quiet, and cool in the night air. That color is the reason people sometimes call these events blood moons, even though nothing about it involves actual blood. It is just atmospheric physics, the same physics behind every red and orange sunset you have ever watched. Except this time, the whole sky is doing the filtering for an object 239,000 miles away, instead of for the sun sitting just above your local horizon. Here's where the underdog story gets even better. This eclipse is actually the final chapter in a run of 4 lunar eclipses that astronomers have been tracking since March of 2025. The first 3, in March of 2025, September of 2025, and March of 2026, were all full, total eclipses, meaning the moon fully vanished into Earth's shadow each time. Scientists call a run of 4 eclipses in a row a tetrad. This one breaks the pattern right at the finish line. Instead of a 4th total eclipse closing out the set, orbital geometry nudges this final one just barely into partial territory, so close to total that astronomers have started calling the whole 4-eclipse run an almost tetrad, because of how this last one falls just short. There is a reason this particular moon looks slightly smaller than usual too, and it has to do with distance, not shadow. 6 days before the eclipse, on August 22nd, the moon reached what is called apogee, the single farthest point in its orbit around Earth for that entire month. At apogee, the moon sits noticeably farther away than at its closest point, called perigee, so this full moon appears a touch smaller in the sky than the supermoons you may have heard about in other months. Smaller and farther away, and still, 96% of it disappears into shadow. That is not a small object doing a small thing. That is real geometry lining up across 250,000 miles. Quick gut check for you. If you have gotten this far, Hit the like button right now and tell me in the comments why an event like this actually matters to you, because that single tap tells the platform this kind of content deserves to reach more people who would genuinely enjoy it. Astronomers also track something called a Saros cycle, which is basically a family tree for eclipses. Every eclipse belongs to a Saros series, a repeating pattern that plays out roughly every 18 years and 11 days, as the Sun, Earth, and Moon slowly drift back into a nearly identical alignment. This week's eclipse belongs to Saros series number 138, and it is the 30th eclipse out of 83 total eclipses that will ever happen in that particular series, a family of eclipses that started centuries ago and will not finish playing out until centuries from now. So in a very real sense, this exact shadow has a long lineage, cousins stretching backward and forward through history, even though the specific moon, the specific night, and the specific 96% will never happen in quite this way again. Let's shrink this back down to something you can hold in your head. Imagine your kitchen at night with just the small bulb inside your refrigerator lit, door cracked open a sliver. That thin blade of light spilling onto your kitchen floor is roughly what the moon's brightness will look like at the peak of this eclipse compared to a normal full moon, which is closer to every light in your house switched on at once. The moon is not shutting off. It is dimming down to a fraction of its usual glow, the same way that fridge light is real light, just a small, dim slice of what your kitchen normally has. And here's the domestic flip side of that same idea. On a night with zero eclipse happening, a full moon is bright enough to cast a faint shadow behind you if you stand under it in an open field, similar to standing near a single street lamp a block away. During totality-level darkness like this eclipse produces, that shadow disappears completely. The moon goes from street lamp to nightlight to almost nothing, all within about 3 hours, and then climbs its way back to full brightness over the following 2 hours, like someone slowly turning a dimmer switch up, down, and back up again over the course of one long night. Here is something scientists will openly tell you they do not fully understand yet, and it is worth sitting with for a second. Nobody can predict with total certainty exactly how dark or how red this moon will look until it is actually happening. Astronomers rank eclipse darkness on something called the Danjon scale, running from 0, meaning the moon nearly vanishes into black, up to 4, meaning a bright coppery orange glow you can see clearly. The color depends on how much dust, smoke, and volcanic ash happen to be floating in Earth's upper atmosphere on that specific night, all around the planet at the same time. A big volcanic eruption months earlier can darken every eclipse for a year or two afterward. Right now, researchers cannot fully model that in advance. They can calculate the shadow's shape and timing down to the second, but the exact shade of red is something we genuinely only find out by watching it happen. This is also a good moment to zoom out to the biggest question hiding underneath this entire video, which is why Earth even has a moon large enough to throw a shadow like this one in the first place. The leading explanation among planetary scientists is called the giant impact hypothesis. Roughly 4.5 billion years ago, not long after Earth itself formed, a Mars-sized object slammed into our young planet. The collision blasted a ring of molten rock and debris into orbit around Earth, and that ring slowly clumped together, over time, into the single moon we see tonight. Researchers at institutions including NASA's Jet Propulsion Laboratory and Caltech have spent years analyzing moon rocks brought back by the Apollo missions to test this idea, and the chemistry of those rocks lines up closely with what a violent collision like that would leave behind. So every time you look up at a full moon, including the one about to slip into shadow this week, you are looking at debris from a planetary collision older than almost anything else in our solar system. Debris that eventually cooled, rounded out, and settled into an orbit exactly far enough away to occasionally line up with Earth's shadow, the way it is about to do again in just a few nights. Quick favor to ask. If any of this has genuinely surprised you so far, share this video with one person who still thinks lunar eclipses happen every single month, because that misconception is honestly one of the most common ones out there, and this is the easiest way to correct it for someone. Now let's talk about what you actually need to do to watch this yourself, because the honest answer is almost nothing. Unlike a solar eclipse where staring at the sun without special glasses can permanently damage your eyes, a lunar eclipse is completely safe to watch with nothing but your own 2 eyes. No filters, no special glasses, no telescope required, although a pair of ordinary binoculars will make the color and the texture of the shadow noticeably sharper. All you really need is a clear sky, a spot away from bright streetlights if you can manage it, and the patience to step outside more than once over the course of about 5.5 hours. If you live in North or South America, this is your night. The eclipse happens up in a dark sky well after sunset, which, according to Space.com's eclipse coverage, makes this the best positioned region on the planet for this particular event. If you live in Europe or Africa, look toward the western horizon, because you will catch the eclipse low in the sky, right around moonrise or moonset, depending on your exact location, which adds a dramatic, almost theatrical look as the shadowed moon appears to hover just above rooftops and tree lines. If you are in most of Asia or Australia, daylight will already have broken by the time this begins, so the moon will simply be below your horizon and out of view, though live streams from observatories around the world typically cover the entire event in real time for exactly that reason. And here's the number that puts real weight behind why you should not skip this one if your skies are clear. According to Space.com, this deep partial eclipse will be the best lunar eclipse visible from anywhere on Earth until New Year's Eve of 2028, more than 2 years from now. There are smaller, shallower eclipses scattered across the calendar in between, but nothing that comes close to this specific combination of depth, timing, and visibility. Skywatchers who study these patterns for a living are treating this less like a routine monthly full moon and more like a genuinely rare alignment worth rearranging an evening for. There is one more piece of this puzzle worth knowing, because it ties the moon's shadow this week back to something happening on Earth every single day, whether or not an eclipse is going on. The moon's gravity is strong enough to physically pull on Earth's oceans, stretching the water into a bulge on the side facing the moon and another bulge on the exact opposite side of the planet. That stretching is what creates ocean tides, the rise and fall of seawater you would notice standing on any beach. During a full moon, including this one, the sun and moon line up closely enough that their poles combine, creating what oceanographers call a spring tide, meaning unusually high tides and unusually low tides along many coastlines. So the very same alignment that is about to drop Earth's shadow across the moon is also, at that exact moment, tugging a little harder than usual on every ocean on the planet. Think about the size difference for a second. The moon is about 2,159 miles across, roughly the distance from Los Angeles to New York City if you measured it in a straight line through the ground. And yet something that size, sitting nearly 250,000 miles away, is strong enough to physically lift the entire Pacific Ocean measurably higher on certain nights, and precise enough that scientists can calculate the exact second its shadow will touch itself this week, down to a fraction of a minute. Small in the sky, enormous in its actual effect on this planet. One more question before we close this out. Are you planning to actually go outside and watch this eclipse yourself, or catch it through a live stream instead? Let me know in the comments which one, because it helps me figure out whether to start covering more live stream links alongside these breakdowns. There is a fourth finding worth mentioning here, one that surprised even seasoned eclipse chasers when the numbers first got published. Most partial lunar eclipses that come in under 90% magnitude barely register with casual skywatchers, because the difference between a fully bright moon and one that is 70 or 80% shadowed is subtle enough that plenty of people glance up, shrug, and go back inside without realizing anything unusual is happening at all. What researchers expected here, based on decades of similar events, was another forgettable partial that would draw attention mainly from dedicated hobbyists with telescopes already set up in their backyards. What the calculations actually produced was a magnitude high enough to visually read as total to almost anyone without specialized equipment, collapsing the usual gap between casual viewers and serious skywatchers into a single shared experience. The compression here is simple. A shadow so deep it erases the difference between watching for fun and watching for science. It helps to think about how this compares with an ordinary evening you already know. On a normal clear night with a full moon, you could read a paperback book outdoors just from moonlight alone, the same way porch lights let you see your own doorstep after dark. At the deepest point of this eclipse, that same outdoor light drops down to something closer to a single candle flickering across a room, present, visible, but nowhere near enough to read by. Then, over the following 2 hours, that candle slowly grows back into a porch light, and the porch light grows back into full moonlight, exactly the way it looked before any of this began. Nothing about the moon itself changes during any of this. Only the light reaching it, and the light bouncing back down to you, rises and falls like a tide of its own. It is worth remembering, too, that every person who has ever watched a deep, partial eclipse like this one, going back through recorded history, watched the exact same physical process you are about to watch this week, just under a different sky, in a different century, often without any way of knowing why it was happening. Ancient astronomers tracked eclipses by hand, centuries before anyone understood gravity, and still managed to predict some of them with surprising accuracy just by counting the days between repeats. What you have now, that they did not, is the exact second-by-second breakdown behind the pattern they could only guess at from patient observation. Same moon, same shadow. A few thousand years more understanding of why it happens at all. Cultures across the planet spent thousands of years terrified of nights like this one before anyone understood what was actually happening. Ancient Chinese astronomers described a dragon devouring the moon and would bang drums and pots to scare it away. Norse legends blamed a sky wolf named Hati chasing the moon down and finally catching it. In parts of ancient Mesoamerica, eclipses were treated as warnings tied directly to kings and harvests, serious enough that entire ceremonies were built around bringing the moon safely back. None of those cultures had the geometry we have now. No satellites, no orbital calculators, no space agencies quietly running the same math in the background of a laptop. Nothing but careful, patient counting of days between one shadow and the next, written down, passed on, and checked again the next time the sky repeated itself. And yet many of them still predicted these events with real accuracy, purely through pattern recognition passed down across generations, centuries before Isaac Newton ever wrote down the laws of gravity that actually explain why any of it happens at all. Step back and look at everything that has to line up for a single night like this one to happen. The moon's tilted orbit has to cross Earth's shadow at almost exactly the wrong moment for it to be called a total eclipse, and almost exactly the right moment for it to look like one anyway. The moon has to be sitting near apogee, farther from Earth than usual, shrinking its apparent size just slightly. Earth's atmosphere has to bend sunlight in that same reddish arc it bends every single sunset, just aimed at an object 239,000 miles away instead of the horizon. And roughly 1 billion people, spread across 4 continents, all have to happen to be facing the right direction on the right side of a rotating planet at the right hour of the night. None of that is coordinated. None of it is planned. It is just physics, running the same rules it has run for billions of years, occasionally lining up in a way rare enough that astronomers give it its own name and its own place on a calendar 2 years in advance. This week, it lines up again, for the last time until the very end of 2028, and then the pattern resets and starts building toward whatever the next alignment happens to be. That is the whole story sitting above your head this week, whether you look up or not. Here is a number to sit with as we close this out. 2 years, 4 months, and change. That is roughly how long you will wait after this week before another lunar eclipse anywhere on Earth looks this deep, this dark, and this widely visible again. 2 years, 4 months, until the geometry of the sun, the Earth, and the moon happens to line up this precisely for this many people at once. At the start of this video, I told you that 96% of the moon is about to slide into darkness, and that number probably sounded abstract, a statistic floating somewhere out in space, disconnected from anything in your actual life. It is not abstract anymore. You now know that number is the difference between a fingernail of bright light and a full glowing plate. You know the exact minute it starts, the exact minute it peaks, and the exact minute it lets go. You know why the color turns copper instead of simply vanishing, and you know that nobody, not even the scientists who calculated it years in advance, can tell you the precise shade of red until the night itself decides to show them. A partial eclipse used to sound, to most people, like the lesser version of the real thing, the eclipse you skip because the total ones get all the attention. That was true for you, right up until a few minutes ago. Now you know that partial is just a label on a chart, and that this particular label is hiding one of the deepest, rarest, and most widely shared skywatching moments most of us will get to see for years. So here's what I would ask of you. On the night of August 27th, sliding into the 28th, step outside, even for 5 minutes. Look up and find the moon wherever it happens to be sitting in your particular sky. You will be looking at debris from a collision older than almost everything else in this solar system, dimming under a shadow cast by the only planet we have ever called home, at a depth that will not happen again for years. 96% of it will disappear into that shadow this week. The other 4%, that thin fingernail of light clinging to the edge, is the part worth remembering. Because even at its darkest, even swallowed almost completely by its own planet's shadow, the moon never actually goes away. It just waits, quietly, glowing red instead of white, for the shadow to finish passing, and for its own light to come all the way back. Look up this week. You will not get a night quite like this one again for a long time, and once it passes, the sky simply goes back to counting down toward the next one.